I will start the webinar with a bit of an introductory round first about ICOS, what ICOS is about, and I know that some of you may be very familiar with the ICOS research infrastructure already, but then maybe not everybody. So a bit of an introductory round of what is ICOS and what are our aims and missions, and then also going a bit more in detail on what are the ICOS stations, how to become one, and what kind of data processes we have in place more in general towards the end of the presentation. Then, of course, the other speakers in the webinar will go more in depth to the technical details of the data process in ICOS. So, to start with, what is ICOS? As said, the ICOS is short for Integrated Carbon Observation System. And in the heart of ICOS is, of course, the aim to provide standardized and open data from 180 measurement stations across 16 European member countries. In this slide, you can see there is a map of the ICOS. You can see that the different colors actually represent the different domains that we have in place in ICOS. So ICOS is a multi-domain research infrastructure. We have stations in 3 different domains: atmosphere, ecosystem, and ocean, and they are reflected in different colors in the map, as you can see in the legend. So as many of you are probably most interested of our ocean stations today, you can see that they are marked in the map with the purple color. They can be either fixed ocean stations that are staying in one place, often buoys or so. And then also we have some ship lines, so ships of opportunity that are mobile stations. What ICOS is measuring is greenhouse gas concentration, so carbon fluxes in our 3 mentioned domains: atmosphere, ecosystem, and ocean. And we have, as you can see, many stations in each of the domains in all of our 16 member countries. Foundations of ICOS are, of course, the long-term data sets that are covering the entire carbon cycle in our all 3 domains. So the aim, of course, is to produce data to support science in finding out and closing the loop, let's say, as it's sometimes referred to, of the carbon cycle across the atmosphere, ecosystems, and marine environments. So as said, the purpose and mission of ICOS in general as a research infrastructure, as I think is the case in many other research infrastructures as well, is to provide high quality data from the infrastructure for a larger use. The more on the purpose of ICOS is to understand better the fluxes of greenhouse gases, also the transport in the atmosphere and also between the atmosphere and, let's say, the marine environments, and in general the carbon cycle, as said, to tackle the climate change and to understand better what is happening, of course, in terms of the change in our climate system. ICOS conducts high precision long-term greenhouse gas observations. Maybe the other speakers in this webinar will be talking more in detail on what kind of data is produced and what do we mean with high precision and long-term greenhouse gas data. But this is more of in a more general level here in this slide. As said, we operate in 3 distinct domains, but also in ICOS, I would say that we aim for many cross-domain actions in many of our projects and other actions that we can facilitate from the research infrastructure. Of course, because we aim to close the carbon cycle, so not only to keep the research and also people in their distinct domains, but also encourage this cross-domain collaboration between the different disciplines, scientific disciplines. In the heart of the idea of ICOS is the standardized data production methods, which ensure the high quality data. So as across our 16 member countries, we have the same standards in place for each domain. They can be found on our documentation on our website and in our various publications if you're interested to hear more in detail what kind of standards we have in place. But the general idea of ICOS is that the measurements would be standardized across all our countries in each domain. As you maybe remember from the map that I showed in my previous slide, there can be several stations from several domains in one country. But then all the measurements in each domain and each station class that I'm also briefly gonna tell later on about are standardized so that the data would be always usable for research afterwards, so it will be comparable. Data is free for everybody and it's available through our ICOS Carbon portal that Alex will be talking more about later in his part. And the data and data products that ICOS produces are used in research and by policymakers as well. About the benefits of being part of ICOS, as if it happens that here today we have some people from the community that may not be yet part of our research infrastructure, but may still be interested in joining. Therefore, I have a few points here to talk about the benefits of becoming an ICOS station or an ICOS member. So, of course, the membership provides all the measurement stations guidance, training, and knowledge exchange on the topics and especially on running the measurements and producing the data. So we have quite extensive support mechanisms in place in the research infrastructure for stations. By becoming part of ICOS, it of course also increases the international scientific networking and also strengthens the scientific communities in your, let's say, institute or your network. If you're operating a station that would be interested in joining the ICOS network. Of course, it advances in the standardization and curation of the greenhouse gas data that you may already be producing in your station if you are working in a station that measures greenhouse gases. So by joining ICOS, then, as said, we are requiring all the stations that join our network to follow the same standardizing schemes that we have in place for our stations in ICOS. Of course, being part of ICOS, then it also provides you the community with support for finding new funding opportunities and also applying for multidisciplinary consortium projects. As said, we are operating in not only in the marine domain, but also in the atmosphere and ecosystem domains. So the community is quite vast, and there are many opportunities to apply for, let's say, multi-consortium projects in the future, because it's easy to find other beneficiaries from the ICOS network from other countries among the ICOS members. Just a little note here also that we sometimes get asked from is that ICOS is indeed a research infrastructure. So ICOS is not a short-term project, but a long-term investment, as it should be seen here. So new stations are expected to stay in ICOS for a long time, so not only a year or two. We are looking for, let's say, even decades of continuation here in some of our stations. Of course, ICOS as a resource infrastructure has not been in place a bit more than 10 years now, but many of our stations have been operating for a long time, even for several decades. So the data is there. So we are, of course, aiming for long data sets, as said. So this is maybe something to take into account if you are considering of joining the ICOS network in the future. Then a few words just about the organizational structure. If your station is considering to join. So all ICOS stations belong simultaneously in both countries and in domains. At the moment, we have 16 member countries in ICOS, and they are listed here. So all ICOS stations, they are forming a so-called national network, as we call it here in ICOS. I know that in some other resource infrastructures, the terminology may be a bit different, but basically just referring to the same thing, which is a group of stations in one of the member countries. And of course, one country can have stations even from all different ICOS domains, or maybe just have stations from one domain. Just depends on the situation on that country. Then, of course, at the same time, each station can be part of one or even more than one domain. So either atmosphere, ecosystem, or ocean. We have some stations that are so-called multi-domain stations that have more than one element of our three domains present. This means that several different measurements are taken in that same station. And they are then also have the thematic centers that support the work for all of these stations, depending on which domain the station belongs to. And yeah, as said, we have thematic centers for all of our domains: atmosphere thematic center, ecosystem thematic center, and ocean thematic center. So these thematic centers support all of the stations in that domain, regardless of the country. What it then takes to add a new partner in the ICOS station network, if some of you are considering maybe to join, or if you know a station, or if you would be interested in becoming part of the ICOS community. Something to start with, good to know, is that the members of ICOS are actually countries and not individual stations. So this means that if your country is not part of the 16 member countries, your station cannot unfortunately join ICOS just yet. The current ICOS countries, 16 countries, are Belgium, Czech Republic, Denmark, Finland, France, Germany, Greece, Hungary, Ireland, Italy, the Netherlands, Norway, Spain, Sweden, Switzerland, and the United Kingdom. And joining ICOS as a country, as you may think, is a process happening in the national level. This means often a ministry level or a parliamentary process, because then as a nation, you join ICOS research infrastructure and not as an individual station. Negotiations for adding new countries to ICOS are, of course, ongoing all the time. We would be very happy to have new countries in our station community in the research infrastructure. If you are interested, if you are coming from a country, let's say, that is not in the list that I just mentioned, you can contact the expert in working as my colleague here in the ICOS head office, called Emmanuel Selmo. He's the head of strategy and international cooperation, and he can tell you more whether there is some negotiation happening with your home country at the moment, and what is the status of it, and if there's something that you may be able to do in terms of, let's say, encouraging your policymakers to maybe encourage your country to join ICOS network. If your country is already an ICOS member, as listed, the procedure of adding new ICOS stations is a process again happening in the national level. So the countries propose the new stations to us in ICOS and not the other way, as sometimes we hear that. Why is not ICOS selecting this and this station? This is not the process. The process is that the member countries actually suggest the new stations for us. So each new ICOS station must be proposed by the member country after the national discussions with the host institution and the national funding body are done. Because there are certain payment responsibilities that come with the membership in ICOS. So there are some related membership fees that the country is paying for each station that is in ICOS. And of course, this then needs to be agreed upon with the network and in the national level on who is the host institution of the station and would they be paying the membership fee for that new station to be added in ICOS. As mentioned earlier, in each country, we have the so-called national focal point of ICOS, who is a contact person for all the different stations in that country, in all different domains. And that is a person to then discuss. Often our focal points are also scientists themselves. They are working in some of the research institutions that are there in the network, and they often are also principal investigators of some station themselves. So they know the network, and they are a good starting point to contact if you are interested in becoming part of ICOS from a station that is not yet part of the country, but part of the community. So the contact info of our focal points can be found from the ICOS website. You can see the link there. You can also navigate it through there with the contact info on our website for each member country. So you can contact and discuss with your national focal point if you're interested in joining. Then a few words about the timetable wise. So in ICOS, we add new stations to the network once a year. And that happens in the beginning of each year. So the first days of January each year when we can expand the network. And we need to have a bit of an advance knowledge of what kind of stations we are expecting to have, because this has implications then in the budget in terms of the membership fees, and so we need this information a bit in advance. This means that if a member country would like to add a new ICOS station to the network, the period for announcing new stations for head office to join is between January to the end of June each year for the upcoming year. So about a half a year in advance, we need to know if there would be a new station joining the network. This means that at this point, when it's announced to the head office, the national discussion should be concluded already by that time. So, of course, the country should have an agreement on how to deal with the let's say financial implications of joining the new station in the network. For example, a new station must be announced latest in June 2026 if they wish to join ICOS in January 2027. Yeah, so this is in general about the membership structure, let's say the organizational structure and joining process for those stations if you know or if you're working in some station that would be interested in joining ICOS. We are of course always very happy to have new stations in the network, and we encourage everybody to join. Then a few words about the station labeling process. I suppose the following speakers will talk a bit more about the labeling process in ICOS and what do we mean by labeling process. But I can maybe say in a very general level here in the beginning that this is the standardizing process that we have in place that I already referred to a bit earlier. As said, the standardized, well-documented, and fair data is the purpose of why ICOS is in existence. So the quality assurance process that we have in place is called station labeling process. And for our process, we have these 3 steps in the labeling, as is described here in the little picture. So this is what then happens if the station has already been agreed to be added in the national network, as described in the earlier slides, and they have been officially joining the ICOS network. Then afterwards, the station labeling process starts. Step 1, what happens there is that the station location is assessed and seen if it's okay and well documented also. There might be some additional documentation on the location and on the equipment already in place or of the station, or if it's not a fixed station, of course, more details on the typical shipping route, or so if that's a mobile station in question. So step 1 is to gather the, let's say, the existent data of the station and the main operators at that point. Then the step 2 is the point of the labeling process, which usually takes, in many cases, most of the time, because this is then the step where the constructing, upgrading the station to meet the ICOS standards that we have is happening. So there's a lot of, well, depending on the station, there may be some construction, upgrading new sensors and testing, and let's say there may be some period of needed just to evaluate if the new sensors are working all right, if the establishment has been successful, and if the station meets the ICOS standards as described in our protocols. So the thematic centers are here in this step very useful for the station staff. They are there to help and assist in the process of new stations during the labeling process, step 2. The thematic center also evaluates the process and sees that can see if it's going all right, if there's some additional assistance needed, etc. And then once this is completed and the thematic center and the station have concluded that, okay, this is going all right, the technical testing is going well, and the data is looking good, the station is meeting all ICOS requirements, then the station will be suggested for labeling in the ICOS General Assembly. And if the station is awarded with a label in the meeting, then that is the completion of step 3. And then the station is officially announced as a labeled ICOS station. So this is the process in general. As said, the labeling is done with the guidance of the thematic centers that we have in place. So each domain has their own thematic center. For the marine stations, we have the Ocean Thematic Center, OTC, to guide the marine stations during the labeling process, and also after that, whenever any help or support is needed. Steve is, of course, here to talk more about that today. And support and tools are always available to follow up on the labeling process and how it's going on. So in short, kind of a bit of a summary slide here, what I've just said. What is the ICOS station life cycle in general? So first, here in the green green part, you can say the process for adding new stations. So the member countries, after the national discussions, if it's been agreed that the new station will be added, then the focal point announces the new to the head office by the end of June each year. The head office will ask all the member countries every year if there are any updates to their station network on the upcoming year. And then the focal point, who is the from that country, one country then says, yes, we have this and these changes for our station network next year. Then this has some implications on the budgets, and head office will complete that. And then, if the budget is accepted in the General Assembly, then the new stations will be added as official ICOS stations to the database and to the ICOS community in the beginning of the new year. So this is the green step here in this picture. So once the new stations have been added, then the labeling process can start, as pictured here with the blue color. So once the stations are officially added, the labeling process starts. And then also the member countries start paying the station-based fees for that station annually. And then they also are officially listed as ICOS stations in, for example, our website. In our map, all the personnel will be added into all the networks and email lists. They can have access to the support from the ICOS community from that point. ICOS also publishes the handbook, that as a good source also for those if you're interested in joining. There's a lot of information of how ICOS operates and what it takes to be an ICOS station. That can be also found and downloaded from our website. Or if you want a physical copy, always just email us. We can send one to you. And then the labeling process starts. So as described in the previous slide, the standardizing process starts in the guidance of the thematic center. And after that is concluded and the General Assembly has guaranteed the station an official ICOS label, then we move on to this third phase, which is after labeling. So the labeling is complete for a station. Then it can be called as a labeled ICOS station in the ICOS station network, and then it starts producing the ICOS compliant data, which is then available for everybody through the Carbon portal. Just a little side note, something that we have maybe noticed across the years is that adding new stations and completing the labeling for a station are two different things, as you can see from this graph. Sometimes even within our community, these two things can get a bit mixed up. But so yeah, these are indeed two different things of adding new station and then completing a labeling. So this leads to a situation, as you may now understand from this picture, that in the ICOS network, we have both labeled and unlabeled stations in place all the time. But they are all ICOS stations and they are part of the community anyway, whether they are labeled or not. Then maybe a few words to start, a head start to the next speakers of this webinar. What happens then after the labeling process is concluded? The station then starts to produce ICOS compliant data, and the data ends in Carbon portal, which is the repository for data and the metadata of coming from ICOS. Then after the station is labeled, it starts to deliver data to ICOS Carbon portal. And then it's providing standardized measurements in our stations across Europe. ICOS Carbon portal also provides centralized data provenance, curation, and archiving in the Carbon portal, and also provides the data infrastructure from stations to user, including some data analysis tools for scientists. So here is a little graphical presentation of what has been said right now. In the top, you can see the measurement stations in our three different domains, both atmosphere, ocean, and ecosystem. And the data is then flowing to the respective thematic center. And from there to the carbon portal, where the users can then access it. Also, in addition to the thematic centers as seen in this picture, we have the central analytical laboratories in ICOS that assist especially the atmosphere and ocean stations in our network and their work in the data provision. From the ICOS carbon portal, you can find the finalized data products as well as the sensor data that is repositoried in the carbon portal. Also, the metadata registry and catalog of services, as well as high performance computing services, can be accessed. Yeah, I think this is what I had to present to you today. I'm very happy to take any questions from you later on.
The data flow is a collaborative work between various people around Europe. Obviously, there is me in Belgium. There is Ingen Shelven, who does a lot of work on data checking and labeling for OTC in Norway. We have a data manager, Hannah Teertart, here in Belgium, and also Charlotte in the UK, who works a lot with our metadata. So this is all a contribution from everybody there. Yep, next slide. So a brief step back into history on what the landscape was like before ICOS came along. There was a global database of surface CO2 measurements, which are the primary variables we measure in ICOS. That was a fairly ad hoc, community-driven, and still is, project. Individual principal investigators, that's what PIs it means there, for stations submitted their own data to SOCAT, where it was gathered together into a global product. Some of the problems with that are there is no data provenance. SOCAT relies purely on what the PIs have done with their data. In terms of processing and quality control, there is no tracking of that. There's no archiving of raw data or anything along those lines. So there's a big gap in the data provenance there. And also there's an awful lot of metadata work and other work required by the PIs, preparing all their work, writing their own code for processing, gathering all their metadata records, and that kind of thing. So when ICOS came along, we have the opportunity, at least within Europe, to try and streamline this a little bit. So we have it, head to the next slide. Yeah. So the goals we set ourselves in ICOS OTC to improve the situation was first to standardize the data flow, which means we can track how the ICOS stations are receiving their data, how it's being processed and quality controlled, and generally having a consistent and predictable data flow for everyone involved. So yeah, we standardized the data processing. We built the tool QuinCe, which has been mentioned a couple of times, and we look at data, which all the stations use. Everyone uses the same software to process and QC their data, which means we know exactly what algorithms are being used for the processing. Everyone's using the same ones. We know what's happened, which also then gives us complete data provenance. So we can check, what quality control has been done, what choices were made by PIs, and have some kind of record of that information. The standardized data flow also means that we can then automate a lot of it because we know what we're getting and we know what's coming out, which means we can write standard scripts to send data to wherever it needs to go, in our case, the carbon portal mostly. But it also means we can ingest data automatically. All of these efforts just reduce the work that PIs have to do. And finally, yes, it just allows us to improve our metadata quality and quantity, which is something we have been lacking and something that becomes more crucial over time. Next slide, please. Yeah, so this is a very high-level overview of how the data flow works for stations in ICOS. Our stations are primarily ships and moorings. So they receive their data either via satellite if they're remote ships, or sometimes we don't have any remote or near real-time access to any of the data, and we actually have to physically go there with the USB stick and pick up the data. I say we, it's the PIs. Um, so that data then gets fed into QuinCe, which is, as I say, is our processing software. It's fed in as raw data, completely untouched, or should be untouched, just as it came off the sensor. That data then is archived at the Carbon portal, which means we have the original data that we can always go back to. That is what ICOS terms level 0 data. For those stations that have the capability to transmit their data regularly, we can have near real-time data processing, which is level 1 in ICOS. So QuinCe will ingest the data as it becomes available, perform some automatic QC routines, and the data reduction, which is the processing, the calculation of the final publishable values, and send those off to ICOS to be published once a day. Typically, that gets updated from stations. Now, that is not final data. It hasn't been thoroughly QC'd and properly checked. So there is the final step of level 2 data where the PIs have done their manual QC. Once they've done that, they submit it to us in the OTC. We will do a quick secondary check on it just to make sure there's nothing obvious wrong. And then it would be published as final quality data. And that goes to the Carbon portal. And also we send it onto the global SOCAT database on the PI's behalf. So that's another service we provide to reduce their workload. Next, please. So why do we decide to centralize this software? As I said, it gives us a well-defined and controlled data flow. We know exactly what's happening at every stage. So conversion of data from its original forms into the final publication forms, all calibrations, calculations, quality control decisions we can track. Again, it removes a lot of burden from station PIs having to run their own code, maintain their own code. And it also means that whenever we make updates, it's automatically available to everyone in the community. So everybody always has access to the latest software and routines to work with their data. Next, please. Setting all of this up has been quite a long and difficult process. A lot of our PIs run on they run on research grants. They are researchers more than data managers and pure data collectors. So there's no kind of standardization in the ocean network. So everyone has, or most people have custom sensors installations. Certainly a lot of the installations are custom. Some people even build their own sensors. So we have to deal with that diversity of physical infrastructure. This also means that a lot of the data formats we receive are completely non-standard. From different sensors, different systems. So we get different file formats. There's an astounding array of different ways to record timestamps and positions and those kinds of things. So we have to deal with all of them. And then how data arrives to us can come in all sorts of different ways, FTP, SFTP, emails, Google Drives. We have all sorts of places where data arrives that we have to deal with. Again, because these are often in research environments, this is not an operational network. So we frequently have changes. Instruments are updated. They get moved to different ships as the network changes and available hardware changes. The people running these stations are not trained kind of data technicians, so how they transfer their data has always been a bit kind of vague, and they might change their data format now and then, or add a new sensor or remove one. So there's been a lot of work trying to get people to at least be more thoughtful about how they do that, so that the data coming off the OCC stations becomes more predictable. And obviously, building that kind of operational approach is taking a lot of training and support. So that is a huge amount of the work we do with every station. Next, please. So as I said, near real-time data production is kind of the first step for the data coming off most stations. So QuinCe receives the data from the station. We configure it with whatever data source that the PI happens to have. We saw those earlier. Every day it will go there, check for new files, upload them into itself, and then it will create the data set, extract the data, do the calibration, automatic QC, data reduction, processing, and then send it off to the carbon portal. So every day there is the latest data from the station available for early checking. Next, please. And then every few months, the PI will come and look at their data in detail. So if their data isn't already in the system, in QuinCe, through the near real-time stream, they will get their files off their platform and upload them manually. They tend to divide their data up into slightly arbitrary time periods. I mean, so quite often, if it's a ferry, it might be a crossing, or a container ship, it'll be one crossing, or if it's on a research ship, it might be divided up by each research cruise. It just depends how the PI feels kind of comfortable and what's logical for how the data is being collected and how their station operates. And, for moorings that just sit in the ocean all the time, it's fairly arbitrary. So the data set of a few months. QuinCe does the data reduction and automatic QC as before. So that's exactly as it was for the near real-time data. The user verifies the automatic QC. We do not actually trust that the automatic QC is perfect. So a person has to actually go in and check all of that, and then obviously does their own QC on top. Once they're happy with the data, they've flagged everything that needs flagging. They're happy that the data is as good as it can be. They will then submit it for publication. At that point, someone in OTC, usually Ingrid or Hannelore, will have a look at the data set and just check over it, have a look at the QC that's been done, make sure the PI hasn't missed anything. If there's anything slightly unusual in the data, they may have a discussion about, what's going on, whether these things are indicative of bad data or just a strange event, which happens an awful lot in the ocean. There's a dialogue, goes backwards and forwards. Any queries are resolved, and then the data is cleared for publication at the carbon portal. Next slide, please. Yeah, so I should have said on the previous slide, I was too early. So once the data is cleared, QuinCe will automatically send the data sets off to the data portal, to the carbon portal, where it is archived and given a PID. Now, at the end of every year, we assign DOIs to the data from all of the stations. So there are 2 data collections that we create every year. We create one per station. So for each individual station, their data for the entirety of that year will be put in a collection and given a DOI. So they have a solid reference for their own data set. We also create an ICOS OTC data collection, which is all of the data from all of the stations in that year. We have an example of this from 2025. And that also is given a DOI. So if someone wants to work with the data from across the ICOS network, they have a single DOI that they can use to cite that. Yep, next please. And then, as I said, the SOCAT global database still exists. We don't want the PIs to have to do all this work twice. So since they're sending us all of their data and all of their metadata, we actually take on the work of submitting all the data to SOCAT on their behalf. So we export all the data from QuinCe in SOCAT's format. We prepare the metadata based on what we already have in ICOS, and we do the submission to SOCAT on their behalf. And obviously SOCAT has its own processes of collating the data and figuring out issues and that kind of thing. So ICOS OTC also acts as the first point of contact for queries between SOCAT and ICOS stations, because we are providing that service for the PIs. Obviously, things can go back to the PIs if we need them to, but we take most of that initial communication burden off them as well. Next slide. ICOS obviously doesn't live in isolation. There is a value chain, which is something that Dorothy Backer has kind of pioneered as a description of where our observations fit into the world. So ICOS is at the kind of the base where observations are made, which feed into global products, which feed into analyses like global carbon budgets, which then go on to policymakers. There is a lot of work going on right now to coordinate this on a global scale. WMO has the Global Greenhouse Gas Watch, which through the Global Ocean Observing System, GOOS, are trying to coordinate a lot of the ocean networks, of which we are one. And as part of that effort, we are trying to create, or it is being created now, a network called SOCONET, which is a global network for surface ocean CO2 data. So in the same way that ICOS OTC is acting as one for European stations, people are starting to build a global one. So we are making sure that we are part of their work and compatible with everything that's coming out of that. And I think one more slide. So a lot of the current work that we're doing at the minute is trying to integrate into the requirements of those global networks. So much of that is around metadata, making sure that all the data we provide is kind of discoverable and make sure it gets into all the right places. So we are currently going through a comprehensive metadata review of everything we're collecting from our stations, whether we're collecting everything that they have, whether it's enough for what we need, or if we need to be collecting more. We are developing metadata maintenance protocols to ensure that we keep this metadata up to date, which again is a huge amount of work, and we need to make that as easy as possible for everyone involved. And also we need to develop ways to kind of automate our integration into these global efforts and make sure our metadata systems are sharing the data properly. So that is a key task for ICOS OTC at the minute. I think that was the last one. It was.
So I'm going to give you a bit of an overview of the current, future, and AI-proof ICOS data and connection also to what Steve just told about connecting to other European research infrastructures in EOS, in ENVRI, EOSC, GEO, and other global data systems like WMO. And so let me first go back to an old slide. ICOS is all about reliable data. Providing it in first instance to scientists, but of course the application is for all this data is that it will inform policymakers and the general public on what is happening with the greenhouse gases and thus climate. We do that by generating high quality observation data. This data should be transparent because, well, the air and the greenhouse gases, they're nobody's property. So we should know what's going on. It influences all our lives. So it should be open data of the highest possible quality. And we should keep all the data there so that we are open for scrutiny to see whether we did everything correct, or we can even do corrections when needed on the processing from the raw to the final data products, because, well, it doesn't end like Steve showed with ICOS data. The ICOS data will go into models and will be evaluated by scientists, and this data goes into other products or models which are used by policymakers for global analysis, for example. So this requires a clear data lifecycle, and Steve already showed a lot on what this means for the ocean. And I will try to show you also a little bit for the other domains and how in ICOS we are quite unique in that we are a multi-domain research infrastructure. We try to merge all this into a common metadata model and offer all this information in a harmonized way and also in interoperable way to the scientific user community so that they can work with the data. And also when they produce more higher level data products, that they also can publish this in the same way through the Carbon Portal, making use of their own tools or of the Carbon Portal tools. I will show some examples of that as well. And all of this is to support biogeochemical science and improve the knowledge and inform on these anthropogenic and natural fluxes of greenhouse gases, detect climate feedbacks, and look at emission trends. And in a clear and transparent way so that nobody can doubt what's happening, of course, with the climate skeptics. What is climate change really happening and why? So about this ICOS data flow, this is a bit a different picture upside down compared to what Maiju showed. Here the measurement station are feeding in the information from the bottom. So they send all their sensor data, the raw data, either through the thematic centers or directly into our Carbon portal. So the raw data, this level 0 data is there. The thematic centers, they pick up the data from there, or they have their own repository. They process all this data. Usually then they do a data reduction. So ecosystem data is often 20 Hertz data that goes to half Audi values. Ocean thematic center also goes to ship track integrated measurements. Atmosphere also hourly values from 2-3 seconds to hourly measurements. And then some of the information is exchanged with the calibration lab because ecosystem and ocean stations, they also need calibration for samples to do calibration. And all this information is exchanged through the Carbon portal in a common metadata model. So we do data ingestion. There are these metadata services where we integrate all the different metadata systems from the different domains, because each domain has its own history of how they sample data, the formats that they use, what kind of metadata they gather, and we have succeeded in making this into a common metadata model, which we expose in a FAIR data repository. So FAIR means that users can find, access, and use the data in an interoperable and reusable way. So the users can also feedback data. So the users are on top. They can get all the data from the Carbon portal, including data that other users also have produced. So you get a very nice system where all the scientists can work together, have hold of all the original data, and also can send back data for the other scientists to build on further. So the most important thing about this metadata is that we use persistent identifiers, which are really needed, and linked open data to make it possible that we have this transparent and open model, and that everybody can use the data and know what the data is all about. So we modeled the data through semantic web, and each item in this metadata model is a persistent link, including the properties of all these items. This is quite complex, but in fact, this is a way to model human knowledge in a computer, in something that machines or computers can understand. And this is all based on the standards of the World Wide Web. Already since 1990, this was formulated, and now we build on top of that. So all the data objects, so the data files actually from the daily data that are sent to the Carbon portal, they have persistent identifiers from level 0 to the elaborated data products, level 3, all use the same systems. And a persistent identifier is nothing else than a URL which points to a landing page. And the landing page contains the metadata, and this metadata is something that people can read. Then it's presented to you as a web page, but machines can say, okay, I want this in another format. I want this in the JSON format or an XML format, or I want it formatted as in some other form which is coherent with some ISO norm for modeling for metadata. And we support several of these metadata standards, so that if you have a different system, you can still talk with our system and get all the metadata information on the data that you need. Part of the metadata is also a link to the data object itself, so that you can do the data download, also can inspect what kind of protocols are available to get the data, etc. What is the data license, who produced the data, and so there's a very rich metadata model behind it, and there's an open way to connect to it, which is standard, in fact, the standard web protocols. So everybody, it's relatively easy to support that, to use that. And so there's some other details here. I think I don't want to bother you with that. But the nice thing about these persistent identifiers and a data object model is that these are in fact links which can be used in any other portal. So our data can also be referenced into another portal or a portal of portals, and only they need to index is the persistent identifier to the data, and then when users find the data, they can just follow the link and end up in the Carbon portal and find all the metadata as produced live through the Carbon portal and can download the data directly. So this is working now since 11 years, and we have at the moment 2.7 million data objects of these data files in the Carbon portal, and each year we receive more than quite a lot, more than 3 million downloads. And this is when we take into account only the ICOS level 1 and the level 2, so the near real time and the final quality control. This is more than 70% of the downloads. So while from the 2.7 million data objects, we have only 11,000 are really the ICOS level 1 and level 2 data objects, which are the most recent versions, because we also do a full versioning. So every day there is a new near real-time data object for ecosystem and atmosphere, which then, as we call it, deprecates the previous version. So in the end, we have 1 million of these level 1 and level 2 data objects, but only 11,383 are the actual latest versions. But they together, some people download this near real-time data daily, have 2.3 of the 2.9 million downloads. Overall, from all over the world, we have 262,000 unique users who download the data. So this is really a very huge community who is interested in ICOS data and actually used it. And as you can see on the map, this is the distribution. So we have a lot of users from Europe mainly, but also from the US, China, and some other regions in the world. And Africa are a few countries only that have no downloads at all. In the map, in the plot on the right bottom, you see that there's actually a huge rise in downloads when you compare 2025 to 2024. It's almost a factor of 6. And we suspect, or know for sure actually, that this is due to AI systems, which, because we have this open system, are able to find our data and download it on a regular basis. And this plot was made in early 2026, so in January, end of January. And you can see that already there this increase is still going on, because already in January we are at 1/3 of what we had last year. So this is putting a bit of load on our server, and we're gonna try to remove by getting some data on which bots and machines are used by AI systems, to give you the number of downloads from actual human users and from machine users, because that would be quite useful to see and to compare also with previous years. So we have fair and easy data. So in 2020, there are these kind of tools to measure how fair, how machine readable and interoperable your data is. In 2020, we were at 65% according to this Fuji tool, and now we are at 96%. So there is only 1 or 2 of these items on which you are tested, which we can still improve. So we have a very reliable system, I have to say. So we have availability of the services bigger than 99.9%, so less than a few hours of downtime in the whole period, 2020-25. So that's also why we are able to serve this new real-time data, and that the data from the stations, when they send it, it's usually arriving right away. So we have the data portal, which is for the users to find data, and we have this is really targeted to scientific users who know what they want. So you can, in a faceted search, you can select by project, by theme, by ecosystem type, by responsible country, by station, by data type, by variable you want to use. You can select all these parameters, combine them, and it will do a query and it will present you with a list of all the data sets that conform with this. So you can say, okay, I want only final quality data from the ocean, from this and this station, and it will show you the latest version of that data. And well, this is an example where you see the list of stations. So we have these in the total here. There were 88 conforming to the selection of ICOS stations for ocean. No, not for ocean. This was a combination. Anyway, so you can drill down. So here, this is an example where we selected near real-time data for the station Zugspitze, and then it turns out we have CO2 and methane, and then you have the latest data set. This was some time ago, but then you can select the data sets, you can press the download button, and you will get the data files if you accept the ICOS data license, which is a CC by 4 data license. You can also in the portal directly look at the data. So here's an example from the oldest station delivering atmosphere data. You can see the complete data series starting in 1972 of CO2 from this station in Germany, Schauinsland. Or on the right, you see an example of a data set with PCO2 from a station from the ocean. And this is also a nice preview. You can go along the track in the map, and then you can see the concentration shown in the time series. And when you go over the time series, you can see where this particular measurement was done. And this is quite a nice preview already of the data before you start to download the data. There's also spatial temporal data. So we have this model gridded flux from the Carbon Tracker Europe versions using atmosphere and ocean and ecosystem data together, combining it all in an optimization to get to the best fitting fluxes. And there are different models and different outputs of the model. And you can all show this and have a time plot on the map. And also when you click on a point in the map, you get the result for that specific variable that you choose with time in that specific location. So we have all this data, and we have also a library which you can call from Python to get access to the metadata and the data, and you can test out and use this library in your own computer, of course, but you can also go to our Jupyter Notebook server where you get direct access to the metadata and data, which is a bit more performant than if you have to go through the internet. So all the data stays locally in the Jupyter Notebook. It's on a server which is directly connected to our data repository, and you can use your favorite language. But if you use Python, you can use our Python library and make use of that to analyze the data. You can even get this other higher level data products which we have in the Carbon portal and use that to do your own analysis. And this is actually a lot used by projects, European projects. Some examples here: COCO2, the ICOS cities, the Avengers, and the Nubicos project. And it's also used in education because you can have students go through some of these pre-cooked examples we have in the Jupyter Notebook, but they can also work on their own assignment and do some analysis with the data. Something more. This is, let's say, the traditional way of how we worked with the data in the past few years. But now we have AI, and AI is putting some challenges to us. AI also needs to understand, and what we do here with our system, with the rich metadata and the open things, is already quite useful for AI. But AI is also a threat because people can use our data or AI, or they can ask AI questions, and then AI will go, or it will say that it goes to our system and then present the results. But it can be fabricated data, so the AI can say, okay, this is what ICOS says, but that's actually not true. That's not what in our data. Well, actually, to say something about how we can go about to that, I show you again here how the linear pipeline is when we go from ocean FCO2 observations to the users. So on the left, we have the measurements. They go into this level 0 raw data. Then the thematic center processes the data. It produces level 1 data. And this final quality control data goes in the carbon portal, and from there it goes to SOCAT, and there it goes to users. The users can also directly access carbon portal. They can put data back in the carbon portal. And this is nice. So we have a strong foundation. Everything is there. But now when AI takes the data from the carbon portal and or users go to another data portal where our data is also indexed, they will get just the numbers. There's no way we lose all the traceability between ICOS, the attribution, the data license, etc. People can just take out the data, dump it on users through AI or not. And this is kind of a danger because then anybody can say, draw conclusions on data which is not actual ICOS data. So we look for a solution. So what we need when people use AI is that we still keep this trust, attribution, and reuse at scale for the ICOS data. And for example, we are working in projects like Entry Up Next, and EU projects and EOSC. There's going to be an Entry EU node on the theme of environmental research. And there we are building a portal where people can find all this data, not only from ICOS, but also from other ocean research infrastructures and other domains within the N3. And the idea there is that they can find all the data and download it. But and that you can, for example, make aggregates, so you can combine data from EMSO, from ICOS, from Argo. You can subset the data and etc. But in this process, when you don't consider this issue of taking the metadata with you, then you break the provenance, the attribution, and also you cannot guarantee the integrity of the data that comes out of the databases. So for this reason, I think we have been thinking about working on that, and also making sure that when the users get this data, they can still reliably cite and verify that this is exactly the data that has been served by the research infrastructures. So this is a bit in a picture. So this is, of course, an AI-generated picture, which is a bit weird. But the idea is here is the current situation is people can download the data, they can get it from some portal, and they just get the floating point numbers representing a flux or the FCO2 in the ocean. But they just have the numbers. They don't have a context. Who measured it, where, when, what is the quality of the data? And the idea is that we change that and that we make a system which delivers everything nicely packaged, where everything has a certificate with the quality. That also there's a kind of a checksum so that you know this is the original data. When you check again, when you have the data, you do the checksum calculation. It's the original data still. And even all the metadata that we package with the system, it has also a checksum. So you can see the original data is there, the original metadata is there. So this is really the data as it should be. But that requires some work because these data systems which allow for this subsetting and aggregation, they're not made to do that. They are made for assuming that the people that use it know what they are doing. And of course, that is usually, and you trust them. But I think it's when we use AI and machine, and everybody can start to do that using an AI system, we have to be a bit more careful. And the idea is for that is that we build on a kind of an existing standard and provide with each call, when people extract data, we provide a data passport for all the Entry or the ICOS data products. And this data passport is going with the data as a sidecar when you do a query, and it contains a verifiable machine actionable trust envelope for each official data product. So it includes a persistent identifier for itself. So again, it is a persistent identifier, so it has a landing page. So you don't have to ship a lot of data when you want to pass on the passport with your data. So to say my data is this, I used ICOS data, and this is the trust passport. This is the PID. That's the only thing you have to pass on. And then, of course, if somebody uses your data again, you have assigned a PID on your data. which includes then also a link to the PID from the passport from ICOS, etc. So you can make a whole provenance chain where you can build in this trust and make sure that everybody knows where the data is coming from up in different layers. And also can make sure that the users of the data that are from a data set, which has been in the data set, which comes from another data set, they still can do the attribution and the license check. So the idea is that this data passport is containing all of the metadata that is relevant for user and use, describing the quality, etc. And that we resolve this by human readable landing pages, so you can check when you have this data and the data passport, you can check on the landing page, is this really the correct data still? And all this metadata is machine readable, and we build on a standard which is developing also in the EOSC framework, RO grade. Some details I will skip because there's all kind of standards we will support in this data passport that are already acknowledged and to which include metadata that we already have in our common portal and also in other metadata systems. So with this system, we make our data AI ready and AI proof. And this is kind of a repeat, I think. I went the wrong direction. So what happens now with the picture that I showed to you before is that we build something on top of what we already have. So we keep this magnificent system of high quality metadata. We built on that a metadata-rich netcdf file format for our data, which includes all the rich metadata that we have. We follow the standard conventions on naming the variables, etc. And then we expose this data as in a technology which is called the ZAR store. The metadata files, these netcdf files, are also available in the common portal. You can use them, you can download them just like any data file. But now we can also use the data directly through this ZAR store, and I have to explain this a little bit. But the ZAR store is ideal for use by AI because you can go to the ZAR store, you can ask it, what data do you have? It can give you all the metadata, and it's very easy, as I will demonstrate shortly now, for AI systems to just go to the ZAR. You only have to give it the URL for the ZAR, and it can find out what data is there. And I will show you the example for the ICOS ocean data, how that works. So here is a comparison for you for reference between, let's say, the standard CSV files, which are used by the ocean to also to distribute our data. netcdf is more structured. It also contains a lot of the rich metadata. And the next step is that we provide all this data in a big multi-dimensional array, which computers can access and download. So ZAR is a practical storage format for large observational arrays. You can put in the ZAR multi-dimensional data, five-dimensional data, also different, together with a lot of the metadata that describes the data. So all the rich metadata model we have in ICOS to describe the data can go in the same ZAR archive to accompany the data and can be used for the machines to understand the data and to analyze it. It's also very efficient. It's made really that you can use it in the cloud. So the ZAR archive, the store, can be on different machines. It can be distributed over the cloud, and you can, but still with the software, you can treat it as one big store where you can get all the data. It's very efficient. It splits up the data in small parts, so it can be always very efficient. And the idea is that you don't download the files anymore, but just do a query on the database and only then get the data that you really need. So you can limit it in time and space, and by variable, say I only want this, and I only want this time series where the quality control flag is of the right value, and you will only get that data. So without that, you have to download the whole shit before. You can just get whatever you want. And this is really optimized for cloud-hosted archives. It's for, of course, it's needed that you have analysis-ready grids, so it's really for the level 2 data in ICOS. It supports parallel workflows, so you can use your high-performance computers. Each part of each core in the high-performance computer can take its own part of the data and process it. You can do this all parallel, so each of the thousands of cores in a supercomputer can work on their own part in the same time, so you can do things thousands times quicker than with a single computer, and it all supports that. And I showed you this picture for the ocean. We also can do this for the atmosphere. It follows the same process. In the atmosphere, we already have this standard format in OPSPEC, NetCDF format. We push then, when there is a release, everything in the ZAR store. Same for the ecosystem. In the ecosystem, we have more than 750 variables in different time aggregations. They also go in the ZAR store, and we just, since a month or so, we have our ICOS ZAR store, and we have everything available, all our level 2 data from all the releases, into a ZAR store for the 3 domains. And how does that work? So here's an example. If you have a cloud code account, which is about 20 euros per month, you can use the VS Code development environment, which is for free. And you can have a Python compiler or a Python interpreter, which is also for free. And then you can ask Cloud here a question here. And I told it, Cloud, do not take any memory, because when I use Cloud, of course, it knows everything that we have been done. But I ask it, don't use the memory. You're a fresh Cloud code instance. Do something for me. I'm a marine scientist, and here there's a ZAR store with this URL. And I would like to see when I can detect algae bloom in the North Sea, depending on sea surface temperature, and how this influences PCO2 at the surface of the sea. Can you find useful data in the ICOS ZAR? And then it churns a bit, and then yes, he looked in the index and he said, okay, there's SOCAT data, which has PCO2. So I will install some packages which are needed to access the ZAR store, and I will do that. So it will make a list of to-dos, what it does, and after 5 minutes or so, it will say, okay, yes, I found that there is this information. There is surface CO2 atlas, there's atmosphere data, there's terrestrial ecosystem, ecoflux, and if I look in the ICOS SOCAT, I see that there are cruises, there is data, and everything has rich metadata described with the let long, the source for the DOI, the citation, responsible organization. And I can also query for the region. So it said, okay, let's take the North Sea, which is about this bounding box. And then, yes, I found a cruise group which is in that region. And in the end, it did some calculations, and then it sees that there are 318 of the 477 cruises hit the North Sea. And most of the measurements are for the Forten Bay and the Simonstiffen ship. Then it makes a list, and then the question is, can you detect blooms from sea surface temperature and PCO2 alone? Yes. And then it detects that there is a record, a textbook signal, and it makes a little Python script which you can do. And then you can ask, okay, I would like to look at that, but I want a nice Jupyter notebook for kind of interactive analysis. Takes another 5 minutes, and then you can, it makes this kind of Jupyter notebook where you get these nice plots, where you can see the algae bloom taking up a lot of, reducing the PCO2, and then here it's CO2 is emitted again in the periods when the algae bloom ends and also the algae die. And then there are other ZAR stores where you can, for example, get meteorological information. So ERA5 analysis of temperature and wind speed. So I asked it, okay, can you then do a flux calculation based on the well-known equations to convert the PCO2 in a concentration, and then said, okay, I will take the Cabal measurements from CO2, which you also have there as the background concentration, to do the differential between the PCO2 and the CO2 in the atmosphere. And then it calculated the fluxes, and it did this. So this is the daily CO2 flux from all the measurements in our bounding box on the ocean. And I will go on to, oh, the picture is gone. Anyway, that is how it works. And so we can do this kind of analysis, which a scientist would have taken weeks, months, maybe, just in just half an hour, thanks to this ZAR, and that we have all this rich metadata together with our data in this machine-readable version. And this is, for example, here on the top right, here, you can see that you only need a few lines to also access this ZAR archive and find all the data that we have, including the metadata. And we are working on some other applications like this EnVUp EV browser, where you can show, because I'm out of time, also have, for example, the Argo floats, do previews of that data, and combine also this kind of CO2 fluxes, which I showed from the model observations, on one map together with the observations from ICOS, from Argo, etc. And you can browse all this data using the same kind of techniques, using the ZAR and the discovery automatically. And we're working on this kind of applications now, which help scientists to quicker do this kind of analysis, show how our measurements are done, of course, for quality control. And also, we are assisted by AI using this, but I think this is very useful. And still, because we have also now built in that when you do a query here, you get a data passport, we can make sure that we also contain all the metadata, give it through to our users, and also make sure that people don't cheat with our data. That's it. So it works. Nothing needs to be changed. Everything we do is incremental. And because we have these solid foundations of the ICOS data system with consistent, persistent identification, fairness, and rich metadata, this will allow us to build a cloud-based, responsible system and empowers everybody, our users, but also the RI facilities to use and explore our own data, and makes us ready for the future.
This will be a very fast run through kind of how a user can use QuinCe to process and QC their data. It's quite an involved piece of software, so we won't go through it in huge depth, but at the end there is a link to a website where you can go and look at some detailed tutorials and things, but this will give us a good introduction. So there's basically 4 steps to doing this. The first is setting up your instrument, configuring it in QuinCe, so QuinCe knows what to expect from your data and how to deal with it. Then we'll look at actually creating a data set, loading in the data, performing the quality control on it, and then how it then gets exported to the outside world. So the first step starts very simply. You just ask QuinCe to create your new instrument. You tell it the name of your platform. In this case, because we're in ICOS, we actually have fixed platform names that match our station names in ICOS, and that means that QuinCe can understand how to deal with the rest of the ICOS data system by linking those together. There's a unique platform code for each station, and then we just give it a name that's the PI can use to understand it. As an instrument, as a system changes over time, it may be that you have to have multiple different versions of an instrument within QuinCe as the data changes. So it's good to be able to name them something sensible. Again, very simple questions that are applicable to all stations, how deep your intake is, and then if you don't have a GPS on your system, which a lot of, say, fixed moorings don't, you can put in your fixed location. Otherwise, it will pick that up out of the data. Then we have this rather alarming screen, which is basically all of the different sensors that QuinCe knows how to process. Again, you just pick the ones you want. In this case, we're on a ship, which uses a fairly standard underway CO2 measuring system. So we pick the options for the marine and the atmosphere. Depending on which variables you pick, there may be more information that QuinCe needs to know. In this case, if you're looking at atmospheric measurements, it needs to know how high above the sea your pressure sensors are, so it can do various corrections to get everything back to sea level. Yeah, nothing too complicated there. Now, as I mentioned before, although a lot of these sensors are standard, the systems that they're installed on quite often aren't, which means we can't predict reliably what kind of data format we get, even if we know exactly what sensor we're using. So what we ask you to do is to upload one of your data files just as a sample, and then QuinCe will have a look at it and try and work out what the data format is. So in this case, it's automatically figured out that there's no file header. We've got one line of column headings and the data separated by tabs. It's usually pretty good at figuring that out, but you can adjust it if QuinCe doesn't quite get it right. But it's just helps us to deal with the multitude of different formats we use. We also support data coming in multiple different files. Quite often, the CO2 system comes in as its own file. The sea surface temperature and salinity are in a separate file. Some of the atmospheric data in is a different file. So if you don't have everything in one file, QuinCe can also deal with that. You just upload one sample of each file and tell it where everything is. So the first thing to do is the really basic stuff, which is dates and times. So basically on the left, we have all the columns out of your file and what the data's looking like. And then on the right, it's all the things that QuinCe needs to know to do its work. So we just kind of fill these in. And basically you grab a column name from the left and drag it across into the right place on the right-hand side. So to begin with, we do the simple stuff like the date and time. If you've got a good date format, QuinCe can usually figure it out, but we have this strange situation with American versus British dates. Sometimes QuinCe can't work that out based on the data it's got, so it has to ask you just to confirm which one you want. So that's that part. But then for a lot of the things, QuinCe can actually figure out for itself what needs to be added. So this system is from a system called the General Oceanics. It does use a fairly standard data format. So QuinCe has programmed into it what the most common formats are, which means it can automatically look at the data file and then assign the columns as it sees fit. So it's managed to do most of them here. It hasn't been able to do the water temperature and the salinity, so those ones we have to do by hand. But basically, you just fill in all of the columns just by dragging them across. So in this case, for the water temperature, we found the water temperature column, which in our case was called intake temp. Again, other weirdnesses we have to handle. Usually, if there's a missing value, it's an empty string or it's a NaN or an NaN, but some people use -999 or something strange like that. So we have the ability for the user to specify those just to help QuinCe deal with them. As well as the specific variables you need for doing the calculation, we also support adding lots of diagnostic information in here. So most common ones are things like water flow. You've got a pump system pumping water through your system. If the pump breaks or, the flow drops off, you want to be able to look at that. So although it's nothing to do with the actual calculations, it will help you understand whether your instrument's working properly. So we can have looks at different pressures and temperatures and voltages in the system just to be able to check all that stuff. Obviously, as an instrument is running, it goes through different modes. It can go to measuring air measurements, measuring water measurements, measuring calibration standards if the system has those on board. There are also things that we just aren't interested in. So when it's running filter test, QuinCe doesn't need to know about those, so we just ignore those. Here you can set all of that kind of thing up. Again, a lot of this is automatic for the well-known sensors, but for custom systems, you can adjust these. The other interesting thing we have to take into account often is that especially on large ships, there is a physical difference in location between where certain parts are. So where the water intake is on the ship is quite often at the front and the instrument is at the back. And then, it may take 2 or 3 minutes for the water to get all the way down the ship to where it's being measured. And we have to take that into account in the calculation. So here you can kind of specify what your physical layout is like. And once you've done that, you've set up your instrument and it's ready to go. If you have calibration gases installed, you add all the details of those in here, and then QuinCe will automatically use those in the calibrate to calibrate the data as it does the processing. So that's just a quick screen showing that going in. This is where you can do some fairly sophisticated stuff with your diagnostics. So you don't have to just look at them. You can specify, say, a valid range for your water flow. And then you can say, okay, if my water flow is out of range, then I want you to flag automatically all of these things that are to do with the water. Because we know if the water flow is bad, all of those values are going to be bad. So if we tell QuinCe that, then it can automatically flag everything that needs to be flagged without you having to go through and do it manually. And you'll see that this is the water stuff, so it actually only affects the water measurements. We also have flow rates in our LICOL, which is our gas analyzer, which will affect the CO2. But because it's in the gas analyzer, we can say, well, that will affect basically everything. So you can specify it down to that granularity. Then once you've set all of that up and configured your instrument, it's just a case of uploading all of your data files, which is pretty simple. Just pick them all off your hard drive, send them all up. If there are any new run types that weren't in your sample file, QuinCe will find them and ask you to tell it what to do with those. There are our uploaded data files. So it just goes through checks, figures out the start and end dates, number of records, and whether it can just detect everything, and will tell you if there's any issues in the files. In this case, we're all fine. So once you've uploaded your data, it's time to create your data set. So as I said before, how PIs choose to create their data sets doesn't really matter. It can be a research cruise, a crossing, it could be a month, a few days, or whatever. QuinCe doesn't mind. It doesn't have to line up with the boundaries of data files or anything like that. It can automatically deal with that. So in this case, we have a very simple instrument with one set of files. So we just selected those files for the range of it. Here's an example with a much more complex system, which actually has data from 4 different files. And as you can see, they all have kind of different time boundaries. So we can just say, okay, just process the data from this period where we have all of the overlapping data. Once you've done that, QuinCe will go off and spend a few minutes processing data. You can sit there and wait and watch it. It's not very exciting. But when it's finished, it will say that it's ready for manual QC. So at this point, it has done a lot of automatic QC. It has done all the data processing, the data reduction, and prepared all the values ready to go. One of the first things we do, as I said, on large ships, there can be an offset between when the water comes in through the intake and when it actually gets to the instrument. And you can see here, between the intake temperature and the temperature inside the instrument, we've got this kind of time offset. And we can adjust for that. So basically, you just zoom in on the plot, pick a couple of points where you know the two values should align. And in this case, it's figured out there's 111 seconds between the two. And you can, if over the course of your data set, you can adjust these offsets as much as you need to. So occasionally it might change over time, depending on how the ship's behaving. So you can adjust that and put in as many adjustments as you want. And then once you've finished with that, you can see our data is all nicely lined up, and QuinCe will automatically adjust all of the data to align everything as it does its processing. Once you've done that, we've got a data set that's ready to quality control. So we have a fairly big screen here, which has a lot of stuff on it. There are 2 plots at the top, which I'll get to in a minute. And at the bottom is the data, all the data from your instrument. So you've got, in this white section, these are all your sensors that the measured variable values. We've got all our diagnostics in the blue section. And then moving across slightly, we have values that QuinCe picks out to actually do the calculations. I'll explain them in a second why they're slightly different to the sensor values. And then at the end, you have all the calculations it's done to calculate the final FCO2 in this case. So you can see that QuinCe will tell you every single step of what it's doing, what it's calculating as it goes. So it's not a black box. You can actually see everything that's happening. So this is an example of why QuinCe kind of makes its own copy of all the incoming sensor values. So this is taken for a mooring where the temperature on the left is measured every few minutes, and the CO2 on the right is measured at a much longer interval. But what this means is that the data doesn't always align up exactly in time. You won't get a temperature value at exactly the same time as your CO2 value. So QuinCe does some interpolation work to actually make all the data line up in this case. So this section is just to show you what QuinCe has actually done with the raw measurements you've got and how it's chosen what it's going to calculate based on. Here are our QC plots. You get two of these. They both work exactly the same. It's just so you can look at data side by side. You can see there are blue points here, which is what the automatic QC has found. You can use these plots to literally plot everything against everything in the data set, however you want to do it. QuinCe doesn't mind. You get some nice numbers here showing you where the automatic QC has found issues, so you know where you need to look to work on your QC. Here's a couple of examples and some special plots. So here we're looking at the relationship between the water intake and the temperature inside the equilibrator system, so you can make sure that relationship is looking good. Here we've got temperature and salinity plotted together, so you can see how they compare to each other. So you've got all sorts of options in how you choose to look at your data. There are no restrictions there. In terms of actually doing QC, if we look at the salinity on the right, there's a couple of points down here that QuinCe has found. This is basically a standard deviation check. We think they're probably okay. Actually, they look like they're reasonable, but QuinCe is not perfect at this. So you can select those data points. And then in our case, we want to override that and say, actually, these values are good. So you can just override this, say, this is good. And then QuinCe will say, okay, fine, you can have those data points back. For our values up here, we've got these three values at the top, which are clearly wrong. QuinCe has flagged those. And in this case, there's a shortcut button. You can literally just say, okay, I accept your QC, and it will just instantly apply that flag. Then what you can do handily is just hide those flags, get them out of the way. So now in our intake temperature, we've got a much better view of the data because those strange outliers are gone, and we can actually have a proper look at our data. Another thing to note is that the only thing you can quality control here are the data coming off your sensors. So all the calculated values like the FCO2, you don't quality control those because the quality control is defined by what's coming off the sensors and everything else flows from that. So in this case, you'll see that the measured CO2 on the left, these are the flags that the automatic quality control has found. And in the FCO2 has been flagged bad accordingly because the CO2 is flagged bad. You can't change the flags in the FCO2. You can change the flags in the CO2. And once you've done that, QuinCe will recalculate everything and reapply all the flags to its calculated values. Going back to our diagnostics, you remember we set up a lot of the information for QuinCe to say what happens when a diagnostic value is bad. So in this case, we're looking at our water flow. And we found a few points here where the water flow has dropped off slightly. So we decide that those are bad. So we flag those, we select them, we flag them as bad. And then as you see, sorry, we'll just go back. So all of this data at the moment is good. And then as soon as we flag those few values, then suddenly all of the other values related to that, the temperature, salinity, the CO2, are all flagged bad. And you'll also, you will see, it's only flagged bad where we said only water measurements should be affected by these. So that's why not the whole sequence is flagged bad, but only ones that are actually affected. Another thing you have to quality control is your gas standards. Obviously, we configured QuinCe to say what the true concentration of the gas standards are, and then it uses those to calibrate based on measuring those gas standards and adjusting them back to the true values. So this is a look at the gas standards. So you'll see here, for the most part, on one of our gas standards, it's within 1 microatmosphere of the true calibration value, and that's pretty good. But you'll see down here, right at the beginning of the data set, there is one value that is way off. And again, if we try and calibrate the CO2 data using that value, then obviously the final FCO2 values will be terrible because the calibration's miles off. So we can flag that and tell QuinCe just not to use it as part of the calibration routine. So the quality control will take some time. It kind of takes a few iterations. So you flag a bunch of things, you reprocess it, you go back and have another look to make sure the reprocessing is fine. Sometimes that will throw up new errors because thresholds for things like standard deviations and outliers and things will change slightly. So it can take 3 or 4 iterations to go through the quality control and make sure everything's just right. But once you get there, QuinCe will say, okay, you've got rid of all of the QC flags. Now you're ready for submission. And then you can click on this little cloud here, and that will send it off to someone in ICOS OTC to check the data. And then that will, assuming that passes that check, it will get published at the Carbon portal and also be sent on to SOCAT. So under normal circumstances, your work in QuinCe is pretty much finished. But what you can do, if you actually want to look at your data yourself in any detail, possibly before it's been published, you can export it and download it to your own machine to look at it more closely. It can be supplied in a number of different formats. We have the ICOS formats. We have a couple of special ones for special purposes. There's the SOCAT format. We've done some experiments with Copernicus, so we have a format for them as well. But essentially, you say, I want to download this data set. You pick the format you want, and then it will give you a zip file. What is in that zip file is start at the bottom with a manifest, which is a little JSON document that's machine readable, but basically lists everything that's in the zip file and some information about the calibrations, the start and end dates, the geographical bounds, all that kind of metadata for this data set is included there. You also get back the raw data files that you first uploaded. So these are the data files that went into creating the data set. And then you have the actual data set files, one for each of the formats you selected. So this is a view of the manifest. It's pretty, you've got start and end dates, you've got details about the platform, when it was last processed, geographical bounds, information about all the various bits and pieces that you might want to know about the data set. And then what actually comes with the data set is not just the published final numbers, but also the QC flags and any comments you put with your QC. I should say that whenever you QC a value and flag it anything other than good, you have to put in a comment to say why it's being flagged. So those comments that go in will actually come out in the data file as well. So that information is kept with the data. And then also we saw earlier that QuinCe sometimes does some interpolation to make values line up. So in this data file, it will also tell you either when a data value has been measured or whether it's been interpolated. So all of the information that QuinCe has internally, all of the calculations it does will always come out with the exported data. So as I said, that's a very quick run through of QuinCe. Here is a link to a website that contains about an hour's worth of tutorials, as well as a bit more information about QuinCe. So if you want to have a much deeper dive into what you can do and how it all works, you can go there. There is also a version of QuinCe running there that is for people who aren't in ICOS, but who have CO2 data to process. That is not linked into the ICOS data flow system. It's completely standalone, but it does enable people outside ICOS to use this software if they want to. So that is also there available at that side. And that's it.